All right, let's talk about being a digital blacksmith. It sounds cool, right? Well, today, that's what we are. We're going to explore how we forge the future, not with a hammer and anvil, but with code and supercomputers. I mean, think about it. How can we possibly know how a brand new alloy is going to perform inside a jet engine before we've even made it? That's the big puzzle we're tackling today.
So you'd think this would be simple, right? I mean, we know the laws of physics, don't we? But here's the thing. Here's the real challenge. Why is it so incredibly hard to predict how a real chunk of metal is going to behave? You know, how it'll bend or heat up or, break out in the real world. The answer, well, it really boils down to one word: complexity.
And that complexity, that's our first big stop. Because, let's be honest, we are not dealing with those perfect, uniform little blocks you see in a physics textbook. Oh no. The real world is, well, it's just a lot messier than that. Okay, so where does all this messiness come from? Well, it's a few things, really. First off, real parts, the things we actually build, have complicated shapes. They're not just simple cubes. And second, materials themselves. They don't act in a nice straight line. Their properties actually change when you put them under stress. And if you could zoom way, way in, you'd see they're not just one solid thing. Nope. They're made of thousands, maybe millions of tiny individual crystals. And to top it all off, you've got all these different forces, like heat and stress, all interacting at the same time. It's like a huge, tangled puzzle of physics. So how do we even begin to describe all that complexity? Well, with math. And right here, this is where we meet the villain of our story. These beautiful, elegant, and precise equations that perfectly describe the physical world, but are, for all practical purposes, completely unsolvable. I mean, this is a huge idea. Everything, and I mean everything, from how heat moves through a frying pan to how a massive bridge holds up its own weight. It's all described by a kind of mathematical code. You can really think of it as the source code for reality itself. So check this out. This equation right here, it's called Fick's law. It looks a bit intense, but what it does is perfectly describe how atoms jiggle and move around inside a solid. Now don't worry, you don't need to solve it. That's not the point. The point is trying to find a direct pen and paper answer to this for a real-world object with all its weird shapes and conditions is, well, it's pretty much impossible. And that really gets to the heart of the problem, You've got this split. On one side, you've got the ideal world of textbooks, where pen and paper work just fine for simple, perfect little shapes. But then you have the real world, with all of its gnarly complexity. And for that, you need a totally different kind of tool. You need supercomputers. Okay, so if we can't solve these big, scary equations directly, how in the world do we get from that pure theory to an answer we can actually use in engineering? How do we cross that gap? Well, we build a bridge. And that bridge, it's made out of something called numerical methods. So what are numerical methods anyway? The best way to think about them is as a really clever strategy. You take one impossibly difficult problem and you chop it up into millions of tiny, super simple problems. The kind of problems a computer can just churn through one after another at incredible speed. Okay, the main trick here, the core strategy, is called discretization, and it works like this. First, you start with your whole complex thing. Then, step 2, you basically chop it up digitally into a grid of tiny, simple little pieces. We call them elements. Step 3, for each of those little pieces, the math becomes way simpler. And then, for the grand finale, step 4, you just let a computer loose to solve all those tiny equations at the same time. Once it's done, you stitch all the answers back together, and what you get is a surprisingly accurate picture of the whole thing. All right, so we've got our strategy. Now for the fun parts. Let's see what happens when we actually put it to work. This is where the magic happens, where all that abstract math gets turned into these incredibly powerful predictive models of the real world. Now, this isn't a one-size-fits-all kind of deal. It's more like a mechanic's toolkit, right? You've got different tools for different jobs. For problems that involve stuff like stress and heat, the go-to tool is the finite element method. For other things, maybe things that change over time, you'd grab a different method. The key takeaway is that there's a specialized computational tool for pretty much any physics problem you can think of. So let's zoom in on the big one, FEM. That's the finite element method. This thing is an absolute workhorse in engineering. I mean, it's used everywhere. It's what lets us see the insane stresses inside a jet engine's turbine blade while it's spinning. It's how we can predict exactly how a sheet of metal is going to bend in a factory press. We can even model the crazy heat flow during welding. Honestly, it's like having physics-based X-ray vision.
And believe it or not, it gets even cooler than that. With methods like phase field modeling, we can literally watch a simulation of individual crystals growing as a piece of metal cools down and solidifies. Or with multiphysics models, we can simulate how a bunch of different forces all interact at the same time. Think about the crazy mix of heat and stress that's happening during 3D printing. I mean, we're simulating reality at a level of detail that was straight-up science fiction just a few years ago.
So, what's the big payoff? What do we get for all this incredible computational muscle? Simply put, it gives us the power of prediction, the ability to see how a material is going to act before it even exists. Now, it's not magic, okay? The advantages are absolutely huge, don't get me wrong. We can run thousands of what-if scenarios on a computer instead of doing costly experiments in a lab. That saves a ton of time and money. And we can see things inside the material, like how stress is distributed, that are just impossible to measure in real life. But, and this is a big but, there are catches. These are always approximations. They're not perfect truths. They can take a massive amount of computing power. And probably the most important thing to remember is that the model is only as good as the physics you put into it. The old saying, garbage in, garbage out, is the golden rule here. So the real skill isn't just building the model. It's understanding its limits and knowing exactly when you can and can't trust what it's telling you. And that really leaves us with one final big thought to chew on. We've built this incredible digital forge. We figured out a way to simulate reality with just stunning accuracy. We can now design brand new alloys for spacecraft, create better materials for next-gen batteries, and invent composites with properties we could only dream of before. So you see, the question isn't really, can we predict the future of materials anymore? We can. The real question, the one we all have to think about, is, now that we have this power, what are we going to build with it?